right, so we've talked about proving uniqueness. Oh, sorry, we've talked about proving existence. Now let's talk about proving uniqueness. So sometimes you want to prove not only that something exists, but so that it's the only one, right? Like when you prove existence, you're just proving that there exists at least one example or one case when the thing is satisfied. But uniqueness means it's the only one. So for any other element besides that, the statement will not be satisfied. So when you're proving a unique existence, first of all, the notation is like this. There exists unique x, so the exclamation point here means unique, such that p of x. And it's really like a two-step process. First, you prove existence, like you do either constructively or non-constructively, and then you prove uniqueness. And the way you do that is you show that for all y with y not equal to x, then not p of y. So essentially, this is showing what this means here is given any y that's if it's not equal to x, then the statement is false, right? That would show that x is in fact the only one. The x that you proved the existence of is the only one. Or you can show that for all y, p of y, if p of y is true, then y must in fact equal x. Now, these two, that's another option, right? And which would actually achieve the same thing. But if you compare the two things that I said, they're actually equivalent to each other because it's just contrapositive, right? So one of them is y not equal to x implies not p of y. Remove both of those nots and make the arrow point the other direction. That's contrapositive. Now it's p of y implies y equals x. So both of those are ways to prove uniqueness. Let's do an example. The example is, for all real numbers, given any two real numbers a and b. By the way, sometimes you'll see for all a comma b. This is equivalent to writing for all a for all b. So this is equivalent to like for all a for all b, like that. You just you can list as many of them as you want for all a, b, c, d, and then elements of the real numbers. This is our domain. As long as a is not equal to 0, okay, then there exists a unique x in the real numbers such that ax plus b equals 0. So it's like there's a unique x solving this linear equation with a and b as its coefficients. And a not equal 0 just makes it so that this is truly linear and not a constant polynomial on the left here. Okay, so let's do a proof. All right. So first of all, we're going to begin by saying let's let a and b be elements of the real numbers, and let's let those be arbitrary. So that's a very important word and a very important sentence in this proof, because saying that they're arbitrary means that a and b could be any two real numbers. Now we have to treat them as arbitrary in our proof. We can't specify what their values are. We can't say, okay, let's have a be 5 and let's have b be 7 or whatever. We're going to call them a and b. We're working with them abstractly. We're just going to call them a and b. We're not going to say what they are. We're going to treat them as if they could be any two real numbers, as long as, I guess we are going to say a is not equal to 0. So let's have that be the next thing. And a not equal to 0. So now I'm going to say this. I'm going to say let x equal negative b divided by a. I'm going to show you that this x satisfies the statement that if I plug this x into this equation, it will equal 0. And this will be satisfied. Now, how did I come up with that? Well, part of writing a proof is figuring it out first and then writing it. So how would you have come up with that? Let's pull out our scrap paper. This is not part of the proof. This is the scrap paper, okay? What do I want? Well, I want ax plus b to equal 0 in the end, right? So what do you think x should be? Well, if I get to say a and b are arbitrary, and then for those a and b, let's find the unique x. Well, that means x can depend on what a and b are. Let's just solve this, right? Let's just solve this. Ax is going to equal negative b, and then if you divide by a, which is valid, remember that's going to be valid since in this statement we're assuming a is not 0, x is going to be negative b over a, right? So see how what I did is I figured out what x would be by kind of working backwards But I don't present it that way in the proof. In the proof, I just say, let x be this, okay? Now, ax plus b is going to be a times negative b over a plus b, which will be negative b plus b, which is indeed 0. So you see, when you're actually presenting it, you do it in the direction where you begin by asserting what x is, right? You state what x is going to be in terms of the a and b, and then you show that it satisfies the equation. As opposed to starting by like saying you want it to satisfy the equation and then figure out what x has to be. You don't do this. You figure it out this direction, and then you present it that direction. Because that direction is the direction the logic flows. This is the direction that your problem-solving process flows, right? But the actual proof needs to go that direction. Okay, so now we have proven existence. Okay, so I'm just going to state for the reader, this proves existence. Sentences like that, including a sentence like that in your proof, is useful because, then when I'm grading it, I'll be like, aha, all right, good. And then I can pause and I can just make sure that you did that right before I move on to the next part. Okay, so now we've proved existence, now we want to prove uniqueness. So now we're gonna, how am I gonna do it? I'm gonna, which way am I doing it here? I'm gonna do this way, I think. I'm going to suppose, I'm going to do it that way. I'm going to suppose that ay plus b equals 0 for just some arbitrary, arbitrary y in the set of real numbers. Okay. So I'm supposing that this is true. It's essentially this. I'm supposing that p of y is true, right? For some arbitrary, and it's arbitrary, which means it could be any of them, right? It could be any y here. Then, well, now I get to do that kind of reverse engineering, backwards thinking like we talked about earlier. Then ay equals negative b. So y equals negative b over a. And therefore, or thus, y equals x, right? Because negative b over a is already what x is equal to. So I showed, if something were to satisfy this, if this y were to satisfy it, y must be the same x that we proved that we found earlier, right? So therefore, that x must in fact be the only one. This proves uniqueness. And that does it.